Good morning.
Okay, so the plan for today is to just work our way through 4-2 graphing linear equations in two variables. And as part of the discussion today, I want to review the WebAssign graphing tool. It can be, a little bit, there can be a little bit of a learning curve to it. So we'll take a look at, after we graph a couple of equations in the lecture and do a couple in practice, we'll jump over and take a look at WebAssign and just review how that graphing tool works. And I've also posted a supplement on Blackboard under the supplemental material folder. You can find a supplement that kind of walks you through some of the different things that you might want to do using that graphing tool. So we probably won't go through all of the details in class today, just give you a general idea. And then that supplement has some more information. So definitely check that out in the next couple of days before you, work through the homework on WebAssign for 4.2. So the quote of the day is, I suppose, actually a meme of the day. I saw this a couple of days ago from an outlet that I follow on Facebook called XKCD. They publish these funny little comics that have to do with usually something like science or math or statistics, something like that. And so this one has a little bit to do with statistics. When it's there's the one guy that says when a metric becomes a target, it ceases to be a good metric. So, a business or entity operating in the market wants to provide value to the market. And they might be asking themselves, are we doing a good job or not? So their target, their goal is, we want to provide value to the market. We want to do a good job in this area. And to help them answer that question, they might come up with a metric. They might say, okay, well, let's find some way to get a number that's more objective that tells us how good we're doing in the market. Maybe that's something like how much market share do we have, or customer satisfaction, whatever it is. And the point of the metric is to say, how are you meeting your goal? But what the first guy is saying here is, well, a lot of times what happens then is the goal shifts to make that number higher, not to, serve the market better. And if our goal shifts to just make that number higher, then the metric becomes a target. And why is that a problem? It might seem like we're just trying to answer the same question or do the same thing a different way. Well, a lot of times the metric can be gamed. So we can, if we target just making the number higher, we might actually be serving the market less effectively. We might be doing our job less well just to make that one number higher. And for some reason, my computer keeps freezing. Sorry, it's kind of distracting me. So I think I might have to restart OneNote. Sometimes OneNote, when it's been open for a little too long, doesn't like to work so well. But anyway, where is this important these days? Well, of course, a metric is a mathematical model, really, right? And that's essentially what we're dealing with and discussing when we're talking about, say, linear equations or graphs or any of this kind of stuff. If we're bringing this into the real world, we're thinking of them as mathematical models. And, we have examples of this these days, like artificial intelligence. A lot of the AI programs, the way that they work is they have a number, they have an objective function that you put a bunch of inputs into it, it spits out one number. And the goal of the AI program is to make that number as high as possible, right? Change all of these weights or all of these other things, or how the thing makes predictions to make that one number as high as possible. And it doesn't think about anything else, right? It doesn't think about ethics or what's the right thing to do or what's the sensible thing to do. It just, says, how do I change my values in this big complicated equation to make this number really high? And just, I think this week or last week, there was another issue with AI and the data sets that were fed into it, and it was kind of doing crazy things. So that's one example we see today. Another example is a little more practical. If you're, say, in your career and you're a manager over somebody, and you say, okay, I want to decide whether they're performing well or not. Or I have a team of 10 people and I want to know who to give the higher bonuses to and who to give the lower bonuses to. Well, if you make their salary or their job dependent on one number, they might, the incentive that you've set up is destroy the business in order to make that one number look good. So we have to be just very careful when we set up incentive structures like that. And looking at it the other way, looking at your boss, if your boss says, I want this one number to be really good, then maybe ask whether they've really thought through the incentive structure they're creating and whether they've really thought through what they actually want out of their employees. So let me just really quick here restart OneNote, because I don't want to have to restart it while we're in the middle of a problem. We can just blame Microsoft for all of our problems. Okay, so moving into the material for class today. And again, the topic we're going to be discussing is graphing linear equations in two variables. So last time we discussed using the Cartesian or rectangular coordinate system, so plotting points on a two-dimensional plane. And we also discussed the idea that if we have a linear equation in two variables, once we make a choice for one of the variables, say y equals 6, typically that tells me what the other variable has to be. So if y equals 6, that implies that x equals 1, right? If I put 6 in for here equals 5x plus 1, this gives me one equation and one variable. I can use my equation solving strategies from chapter 2 to solve this for x and to say what x has to be, and that's 1. I could go the other way as well. I could say if I want x equals 3, what value of y do I have to choose to make these two sides of the equation the same? That would be 16. So we discussed all of that last time, and this is actually the same problem from last time that we're just going to build off of. And I said I could think of this statement that if I choose x equals 1, then y must be 6. I could think of that as an ordered pair, 1, 6. We talked about ordered pairs as well in the Cartesian or rectangular coordinate system. Another ordered pair, 3, 16. A third ordered pair, 0, 1. Okay, so what are we building up to here? What I mentioned last time also is I, in this case, maybe chose 3 values for x, 0, 1, and 3, but I could have chosen a whole lot of values for x. That would have given me a bunch of associated y values and a bunch of ordered pairs. These would all be solutions to this linear equation in two variables. When I have a linear equation in one variable, 3 equals 2x plus 1, x equals 1, I can just write my solution algebraically like this, x equals 1, and that's the solution. That's pretty much the end of the story. But how do I convey that there are infinitely many solutions, that there's a ton of solutions for different choices of x and then their associated values of y for a problem like this? Right. How do I represent this infinitely many solutions? Well, one convenient way to represent these infinitely many solutions collectively is I could make a graph. I could make a pictorial representation of these solutions that will convey some information kind of similar in nature to this, x equals 1 solution for my linear equation on one variable. There are pluses and minuses to using a graph instead of an algebraic structure, but I can at least convey the fact that there are going to be infinitely many solutions. So let's set up a coordinate plane. I have an x-axis and a y-axis, and by default, I just pick x to be horizontal and y to be vertical. And then I see that I have a few coordinates here. I can think of these solutions 1, 6 as an ordered pair 1, 6, representing a point in this plane. Now I might do something like, set a scale like this. When I'm going to be plotting a few different points and I don't have an axis given to me, I want to look ahead a little bit. So, okay, I want x is going to have to go between 0 and 3. Y is going to have to go between 1 and 16. So I want to choose my y scale a little differently, my x scale maybe a little differently. Just to make sure that I can fit all of these points on there. So if I'm going from 1 to 16, maybe I'll put 3 tick marks, but I'll go in increments of 5. And then 16 will just be a little bit above that third tick mark on the vertical axis. Okay, so one point is 0, 1, x equals 0, y equals 1. That's maybe here. A second point is 1, 6, x equals 1, y equals 6, maybe about there. And a third point, 3, 16, x equals 3, y equals 16, maybe about there. And I noticed that, up to my artistic abilities, these 3 points lie on the same line. Now, any 2 points, if I come over here, any 2 points are going to lie on the same line. 2 points define a line. If I plot 2 points, I can always draw a unique line through them. But a third point might or might not lay on that line. Right. So realistically, we could plot any 2 of these 3 points, and then that would tell us what direction the rest of the solutions are in. So I noticed that by plotting these 2 points, if I drew a line through them, I'm going to cheat here a little bit because my artistry is not perfect. But if I drew a straight line between, say, these bottom left 2 points, they point at this third point, 3, 16. And in fact, if we had looked at, say, the coordinate associated with x equals 2, if I plug in x equals 2, I get y equals 10 plus 1 is 11. Where would 2, 11 be? It would be also right on this line. So we call these equations linear equations, in part because all of their solutions, all of these ordered pairs that represent solutions to this linear equation in 2 variables, lie along a straight line. So if an xy pair is a solution to this equation, y equals 5x plus 1, if an ordered pair is a solution to that, then that ordered pair will be on this blue straight line here and not anywhere else in this coordinate plane, and vice versa. Any point that is on this blue line here, if I interpret that ordered pair as x, y, that will represent a solution to this algebraic equation here. So two numbers, x and y, are solutions to this equation if and only if their ordered pair lies on this straight line. So for instance, if I look at this red point here, this might be something like -1, comma. So if this is 0 to 5, this is maybe -5 here. So -1 for x. My y solution, just looking at the graph, should be a little above -5. Now, this is one of the downsides of a graphical technique is, well, a little above -5, is that like, is it basically just -5? Is my picture just a little bit off? Is it -4? Is it -4.5? Is it -3? So it's not super precise to go this direction. But if I plug in -1, I see y equals -5 plus 1 is -4. This is in line with what we expected from the graph. So we can plot a couple points on the plane, draw a line through them, and then that line is a representation of all of the rest, including these, but these plus all of the rest of the solutions to that equation. And so I'll just write that out. This line that we think of as just a representation of infinitely many ordered pairs represents all solutions to y equals 5x plus 1. Or we would typically just kind of phrase this something like, this is the graph of y equals 5x plus 1. But this is a way that we can represent these infinitely many solutions. Obviously, we can't enumerate them. We can't write them all out in a table. We can't write them as simply in an algebraic structure as something like x equals 1. So drawing a graph of those solutions is a way that we can represent those infinitely many solutions. Okay, so let's do one more of these, and then we'll jump over and do a couple of practice problems. So here we have similar question from last time. Fill in the following table for the equation and graph this linear equation in two variables. So I have some different x's with associated y's. 0, 6, 2, 2, and 5, 0 are my three ordered pairs. And again, I always kind of keep in mind that this is a sampling of the solutions. So I always keep in mind that there are more, but I've just taken a few to work with to get my graph set up. I plan ahead a little bit. I see that, okay, the x values go from 0 to 5, the y's from 0 to 6. Let me zoom this in a little bit. So I have 1.0, 6. I have a 0.2, 2. And I have a 0.5, 0. Now, unfortunately, if I look at these, I see a bit of a problem. I mean, I'm not a great artist, but it sure as heck looks to me like I don't have 3 collinear points, right? That's a bit far off even for my lacking artistic skills. What would I do in this situation? Well, I'd want to check my work. I know that this is a linear equation. This is in the standard form, ax plus by equals c. Clearly a linear equation. Is 0, 6 actually a solution? X equals 0, y equals 6, 6 times 3 plus 0 is 18. Sorry, my dog is barking in the background. Is 2, 2 a solution? 3 times 2 plus 6 times 2, 6 plus 12 is 18. Is 5 comma 0 a solution? Well, if x equals 5, y equals 0, I have 30 plus 0, but that's not 18. So I actually have a mistake here. So when y equals 0, 6x equals 18, this actually should be 3. So this graphing technique can also be a method of checking our work. So let's X out this one. If I have 3, 0, okay, now, I mean, my artistic skills aren't the best, so it's not perfect, but this is much more believable, right? So if I go to plot my 3 points and they're not on a straight line, if I had just done my 2 axes, 0, 6, and initially 5, 0, I'd have gotten my 2 points, I'd have plotted my line, I'd have moved on, but that would have been the wrong answer. So the third point acts as a check to make sure that the other work was correct. Right? It would be quite rare for you to say get one of the points correct, get the other 2 points both incorrect, but somehow still have them all collinear. That would be, that would be a pretty rare thing to happen. If you do that, play the lottery that day, I guess, because rare things are occurring that day. But we see that, okay, we corrected our point over here. Can get rid of that one. And this is our graph for this equation. This line here represents all of the solutions, x and y, that we can plug in that will give us a valid solution to this equation. And again, if a xy pair is a solution to the equation, it must be on this line. And for every ordered pair on this line, x comma y is a solution to the equation. So these solutions to this equation, sorry, xy is a solution to the equation if and only if it is an ordered pair on this line. Okay, so any questions so far? Okay, so let's work through these two then. These should look familiar from last time. These are the same two tables from last time. I didn't throw in the curveball of putting, a wrong number or something in here, but just for practice, go through, fill out the table again, and then for each of these, and then draw the graph for each of them. And we'll take maybe about 5 minutes to go through these two, and then we'll come back and go through the solutions. Take about 5 minutes, work through these two problems, and then we'll come back and discuss. Okay, so let's work through the two answers. For the first one, we see we get the three ordered pairs 1, 2, 5, 14, and 1/3, 0. And for 1/3, 0, we might look at that and say, maybe that's not too nice of a point to try to plot, or we might just go with it. We might say, well, I have a point on my y or my x-axis that's something like here, y equals 0, and that happens to set x equal to 1/3. So the y value is nice, but the x value is not so nice. Or we might take the approach where we say, that's kind of annoying, especially if we were, say, trying to plot this on WebAssign and the points like kind of naturally want to fall at the integer values or something. Maybe I would just pick a different value for x, like say x equals 0 and y equals -1. That might be a nicer point to plot. What do I need? I need -5 down here. So x equals 0 and y equals -1 would be, maybe something like that. So either way that you wanted to go about it, I think would be generally speaking fine. But for some things, like maybe on graphing a WebAssign or something, you might want to be a little more strategic about which points we pick. But we could, in theory, use any of these points. The other 2 points aren't too bad. 1, 2. So here's x equals 1. I want to be careful because my 2 axes are on different scales. So x equals 1. And y equals 2 is like maybe something like there. And 5, 14, x equals 5. And the y value is going to be just below that 15 tick mark over here. And again, my drawing skills aren't perfect. My axes aren't perfect, but that looks pretty good, right? In theory, all of these points would be exactly on the line, but it's just the limitations of my drawing skills, my ability to draw a perfectly straight line or to make my tick marks on my axes perfectly spaced apart. Those kind of things throw it off a little bit, but we can see that it definitely looks like these points are on this line. And again, this line would represent all ordered pairs that are solutions to y equals 3x minus 1. And we can do the same thing down here. We have 3 points, 3 ordered pairs, 0, 2, 3, 3, -6, 0. So I need to be able to identify x values from -6 to +3 and y values from 0 to 3. So I just chose these axes. Everything is just going in 1 unit on the tick mark. So I didn't have any big numbers like the y equals 14 up here where I had to maybe adjust my scale. So everything is just going in units of 1 in both directions. X equals 0, y equals 2. That's the first point. 3, 3. And -6, 0, the third point. Do these look like they are on a straight line? I think they do. And again, every point that's on this line represents a solution to 6y minus 2x equals 12. And every solution to 6y minus 2x equals 12 is a point on this line. So there's a one-to-one correspondence between those two ideas, the algebraic side of things and the graphical side of things. Or this line is a perfect representation of the solution set to this algebraic equation here. So this can be a little bit abstract. We're drawing, people say, well, when we're using letters to represent numbers, that's kind of abstract. But now we're actually drawing pictures to represent numbers. That can be even maybe a little bit more abstract. But the key idea, I think the key thing to remember is, why are we doing this? there are so many things that maybe seem strange until you really dig down and you ask or you remember, why are we doing this? And that really, I think, helps sort things out sometimes. And the why are we doing this? Because I don't really have a good way to represent infinitely many solutions. I could pick X any way that I want. And once I pick X, Y is determined, but I could pick lots and lots, infinitely many choices for X. How do I represent all of these solutions? How do I can't just list the ordered pairs. So I have to use a different technique, and that technique is to use a pictorial representation of those solutions. Right. It's a little bit analogous, in my mind anyway, to the difference between representing, say, something like X equals 1. I can represent that easily with an algebraic structure, but something like X less than 1 might be nicer to represent as a graph. I mean, if we think X less than 1, like this graph represents those infinitely many solutions. This is a similar concept. Okay, let's look at how to do these problems on WebAssign using the graphing tool. Let me switch my screens around here. Just get myself a little more working area over here. And bring up WebAssign, and then I'll switch my share over. If you want to, in the meantime, bring up section 4.2 in WebAssign, you can kind of follow along. Your specific numbers might be different than mine, but you can kind of follow along with me as I work through a couple of these example problems. So just give me 1 second here to get my windows rearranged. Okay, so I'm looking over here on the left now. This is the section 4.2 homework, but this graphing tool will be used in a couple of different sections. And we see the problem statement: graph this linear equation by plotting points. Okay, so the first thing I would like to do before I actually get into how the graphing tool works, let's actually figure out some points that we want to plot. So y equals 3x plus 5. I'm going to choose a couple of points for x. Let's say 0, 1, and 2, and then find the associated y values. Y is 3 times 0 plus 5, or 5. X equals 1 gives me y equals 8. X equals 2 gives me y equals 11. So I'm looking at the 3 ordered pairs 0, 5, 1, 8, and 2, 11 as 3 samples from that infinitely long list of solutions. And I'm going to use these to help me plot the solution. So there's a couple of things to note here. We want to graph a line. So a line like this, if I was being more careful about how exactly I drew this, I would put arrows on both ends here. A lot of times when we're drawing graphs by hand, we don't really include the arrows at the end. It's just kind of implied that it keeps going off the 2 sides of the graph where I ended it. But if we wanted to be a little more explicit, we could put arrows at the end just to make sure that that is indicated. There are situations where we might have 2 points, and we might only be interested in a line segment connecting those 2 points, and I don't want it to keep going on either end. Or there might be other instances where I have 2 points and I have a directional quantity, like say velocity, where I'm moving in a certain direction, and I only wanted to go one direction, but not the other. So this we would call a line segment. This we would call a ray. But importantly, neither of those are actual lines like we're drawing here. That can be the first thing to realize is when we click our menu here to draw a line, we have on the right side a chunk of a line that is bounded by 2 points. That's a line segment. That's not what I'm looking to graph here. Our middle option is a ray that's bounded by a point on one side but goes out forever the other direction. That's also not what I'm looking to plot. Some folks will use the ray tool in one direction and then turn around and kind of make a second ray. Oh, how did that happen? Make a second ray in the other direction. And WebAssign really doesn't like it when you do that. It sees this appropriately. It sees this as 2 rays and not a single line. So we don't want to do that. I have written to WebAssign about this. I've written to our reps about it. But the way that we indicate a line segment, when we click this drop down, so to speak, it's confusing because it looks like there are only 2 choices. But actually, this first choice here, this first block, which did not change. So when I click the menu, that first block icon stays the same, but that's actually, once you click the menu, that's a choice that you can make. So if you saw that, I could have chosen a line segment. I could have chosen array, but I also could choose a line. So the way that I do that is I click the drop-down menu and then just click the same spot to choose the line. It's bad user interface, so I apologize for that. Like everything else that you do that has a file menu or something, let me see if I can bring one up here. Well, this is, but you know, if you click on something, the drop down that you get, I'm trying to click on something that will give me a drop down, and of course now nothing works, but if you click on something, you know, if there's a file menu, you click on it and then the options to choose are all strictly below the thing you clicked on. That's the interface that we're used to using. The interface on here is just a little bit wonky. Like I said, I did mention it to them. I don't think it will be that big of a change for them to make, but unfortunately they haven't made it. There are other things like this option down here, plotting a point. Now, if I do something wrong, if I, you know, chose the line segment option and plotted a line segment, and I say, oh, wait, I didn't want to do that. I have a couple options. I can delete one item. If I, you know, have some complicated thing that that I want to get rid of, I can clear all. And it'll pop up and say, you sure you want to clear everything? Yes. Or I could come over here and just click the X to get rid of the individual thing that I want to get rid of off of the graph. Now, what if I draw a line and I say, oh, wait, I drew this line, but I clicked a slightly wrong area. Do I have to sit here and draw the line 10 more times until I can click exactly right? Well, no, not necessarily. I mean, you could, if you wanted to, you could delete it and redraw it. But if you see where it says line 1 over here on this graph layers list, there's an arrow to the left. You can click that arrow, and this dropdown will tell you the characteristics of this line. Maybe for a future, you know, section or a future course, you want to make it a dashed line instead. But I can also change the points here. So I say, oh, I didn't want this to be -6. I wanted it to be -5.5. That would have been hard to click over here, but I could click, you know, somewhere close and then adjust if I need to, just by typing in the X and Y coordinates for the 2 points that I'm interested in. I'll just get rid of this. Okay, so for our particular problem, we're going to choose 2 points to plot the line, and then we're just going to check the third just visually. So let's go to our line plotting menu, click the same spot that started the dropdown. So we're going to plot a line now. I want 0, 5, x equals 0, y equals 5. That looks like that point. And 1, 8, x equals 1, y equals 8 looks like that. I can double check that where I clicked was actually, I actually ended up exactly where I wanted to be. That's not just, I'm not 0.1 off or something like that. I can double check 0, 5, 1, 8. That looks good. And then I can visually check. I don't want to draw anything else in this picture. So these are the two that I used to plot. And I can visually check is 2, 11 on my line. And it does, I mean, it's all the way up here at the top, but it does look like 2, 11 would fall on this line. It seems to me like I did the algebra and arithmetic right. It seems like the plotting went well. I can submit my answer now. And I see that it's marked correct whenever I get this little check mark in the bottom here. This submission data sometimes is helpful. Like here, it actually is a pretty helpful text. So if you got an answer incorrect, let's say, we get on here and we submit the answer. I can look at my submission data and say, maybe, oh, I meant to do -7, 2, or I meant this to be -8.5, and it looked like it was close, but maybe I need to come over here and edit my line, -7. So if you notice that, whenever I changed the -8 to say -7, it automatically updated the line. And then I could just resubmit. Right. I mean, obviously I didn't go through the work for this one, but I could edit my points. And once those points are the points that I want them to be, I could just come down here and submit again, and it would update everything. Or if I wanted to, if I wasn't happy with this, I could just get rid of the line, clear all, delete whatever method you like best, and then just start over and, start the problem again. Something that I don't want to do is I don't want to plot extraneous stuff. So if you were drawing a graph by hand on an exam or something, and you had this graph up here, if I said plot 2 points and draw a line, if you plotted these 2 points, drew your line, and then plotted this point just to check, no big deal. WebAssign is a little pickier. So if you go, say, plotting extraneous points, even if they are correct, even if they're on the line, sometimes it will not be happy with this, right? I have a couple extra points over here in addition to the line. Sometimes it picks up on that and says, oh, you plotted a whole bunch of other stuff. I only wanted to see one line that has this relationship between each of the 2 points. So that's how it's going to check it in the background. It's going to say, is there one line and only one line plotted? And the 2 points that the line goes through, do they follow y equals 3x plus 5? If the answer to all 3 of those is yes, the problem's correct. If you plot extra points, at best, the behavior is unpredictable. If you want to plot an extra point like this, just so that you can say visually see that you've done things right, that's not really a problem. Just make sure that you go and delete those before actually submitting the problem. So if WebAssign asks for a line, the only thing you should see over in graph layers is a single line. In some later sections, maybe we might graph 2 lines on the same plane. Then you should see, line 1 line 2, if I wanted the graph, say a second line for a future topic. Okay, here's line 1, here's line 2. But again, I don't want to go plotting extra points or anything like that. If you say, how do I tell the difference between a line versus 2 rays? What if I had mistakenly done this and this, trying to get that to turn black. So how can I tell that this over here on the left is not a line, but is actually 2 rays kind of back to back? Well, one thing, if I hover over it, you'll notice that the thing that the structure that I'm interested in kind of turns from black to blue. And I can see that only half of this quote line is turning colors at a time. That's an indication that this probably isn't just one straight line. I can also look over here and I can see, oh, okay, I have ray 1 and ray 2. So clearly I have a couple of rays, these kind of one directional lines, and that's not what I'm looking for. So I can get rid of those and then plot my line if I need to. So I think those are the main things that are really kind of the learning curve with this. Is the biggest thing is this strange user interface where you click the line drop down menu and then the first icon stays over top of the menu name, basically. So you have to click that again. I mean, when you get used to it, it's just click, and then you draw your line, no big deal. But for the first few times you do it, it just feels strange because that's not the way that we're used to interacting with drop-down menus. And then the second thing that people, that causes people hassle, and of course there's not a nice point on this line, but is adding extraneous points or extraneous information. You might have the correct line somewhere on the graph, but if it's asking you for one line, it's looking for one line. If there's a bunch of other stuff, it's probably going to end up marking it wrong. Okay, so just go through and be careful about what it's asking for. The other thing to note is that we could have horizontal or vertical lines, and those work just the same way. So nothing special to draw a horizontal line or a vertical line. Yeah. Are there any questions about this WebAssign graphing tool or any of that? So I think mainly if you remember those two things, don't plot a bunch of extraneous stuff on your plot, and just this little goofy behavior of this drop-down menu here, that this first choice is the one that you're usually going to be using. We don't do a whole lot with rays or line segments in this course. So this first option is the one that you're going to be using most of the time. If you remember those two things, I think that clarifies most of the questions. And then that supplement has, basically a recap of all the stuff that I talked about and a couple examples as well. Okay, so let's work through a couple more problems. And we're actually making really good time. I thought we were going to spend a little more time than we are. So let's work through a couple more problems. Find 3 solutions for this equation and graph. And again, we did look at this one last time, but let's recap how we might approach a problem like this, where we don't really have a table set up for us. We have to kind of set up our own table. I have to pick a few values of X and find the associated Ys, and I would like to pick them in a way that I get points that are pretty easy to graph. I don't want to pick like x equals 1,000,000 or something that's going to be like way off the right side of any normal graph. I want to pick reasonable x values. I want to pick x values that I think are going to give reasonable y values. So a little bit of strategy, a little bit of strategy here. What is that? Like strategy? I was going to say strategization, but I don't think that's a word. So some strategy here, and sometimes we pick an x coordinate, we get a y coordinate, we say, I really don't want to graph that one, I'll pick a different x. So x equals 0 is usually a pretty good one to start with. When x is 0, we can see that y is 8 pretty clearly. A lot of times I want to also know, so x equals 0, y equals 8 gives me the coordinate on the vertical axis where the line crosses. A lot of times I also want to know the coordinate on the horizontal axis. When y is 0, when we're on the x-axis, where does the line cross the x-axis? So if I have 0 equals negative 2x plus 8, well, that means 2x equals 8, x equals 8 over 2, x equals 4. Okay, that's not a bad one either. So I have my, what we call two intercepts, my x and y intercept, where the graph of the linear equation intersects the two axes. And now I probably want to choose an x, say, between 0 and 4. That might be kind of sensible. If I choose something like x equals 2, I think that's going to give me a reasonable answer. I'm going to get y equals 8 minus 2 times 2, or y equals 4. I need a little more room up top there. And remember that with graphs, we're kind of like splitting the difference between the precision of an algebraic statement, like x equals 1, that's a very precise statement. Or like in geometry, if we draw a triangle or we draw a rectangle or something, we really don't mean to imply by that picture, by that diagram, any information about, say, relative side lengths or relative angles or anything like that. It's really just a diagram. In a graph, we want to be pretty reasonably accurate with, drawing axes that are perpendicular, with making sure that our tick marks along each axis are roughly equally spaced. So we want to be fairly accurate so that we can make educated guesses for other solutions based on the line. But of course, we realize that, this isn't going to be perfectly accurate. It's not going to have the precision of an algebraic answer, but it should be a lot more precise than like drawing those diagrammatic representations of rectangles or circles or triangles that are not meant to be really precise at all. Okay, so I have 3 points. Let me graph 0, x equals 0, comma 8, y equals 8, 4 comma 0, x equals 4, y equals 0. That's where the line is going to intersect the two axes. And then 2 comma 4 acting as a check. And here's my straight line. And just to be a little more careful, I will put the errors at the end. So this line goes on forever. I could plug in x equals 1,000,000 and get whatever number I get out of there. And again, I could also say, well, when x equals 3, what do I think y is? Maybe y equals 2. Does that make sense? 8 minus 2 times 3 is 2. Right. So I can make an inference based on this plot here, what the associated values of x and y are for different choices of x or y. And similarly for this next one, if I plug in x equals 0, again, looking at where my graph of my equation is going to cross the axes, I get 2y equals 15, or y equals 15 halves. If I look at where y equals 0, I get negative 4x equals 15, or x equals negative 15 fourths. Not very nice answers, right? I see that my left side, for any integer choice of x and y, any integer choice is x and y, is always going to be even, right? This is like, we could think of this being like 2 distributed into y minus 2x. If y and x are integers, this is going to be an integer multiplied by 2 makes it even, and my right-hand side is odd. So I know that I'm not going to be able to pick x's and y's that are going to be super nice ordered pairs for this. But I'd rather probably deal with halves than quarters. So, okay, so if x is 0, y is 15 halves, so 7.5. If x is what, maybe like maybe negative 1. Why did I pick negative 1 for x? Well, when I do minus 4 times negative 1, that's going to give me a plus 4. I'm going to subtract 4 off of both sides. That's going to bring this 15 down to an 11. That's a more manageable number. If I used x equals like plus 1 or plus 2, then I would be adding more onto the 15. That's going to make that a bigger number. So then I have 2y minus 4 times negative 1 equals 15. 2y plus 4 equals 15. 2y equals 11, or y equals 11 halves. So negative 1 comma 11 halves. I kind of don't want to use this negative 15 fourths, so let me try to find a third ordered pair that only has integers or halves instead of quarters. If I go to x equals negative 2, 2y minus 4 times negative 2 equals 15. 2y plus 8 equals 15. Subtract 8 from both sides, and then divide by, so that's 2y equals 7, divide by 2, y equals 7 halves. Okay, so I have 3 ordered pairs. Again, they're not nice integers, but I'm not going to get nice integers here. But I have 3 ordered pairs, and kind of the worst fraction is a half. So this might not be too terrible to plot. Let me actually make this a little bit bigger, since I'm going to be drawing halves on here. Make it a little easier for you to see. Okay, so x goes from 0 to negative 2. And then y, I want to go up to 15 halves, so 7.5. I still need a little more room up top here. Okay, so I have 0 comma 15 halves, 0 comma 7.5, which is there. I have negative 1 comma 11 halves, so negative 1 comma 5.5, between 5 and 6. That looks about right. And negative 2 comma 7 halves, negative 2 comma 3.5, between 3 and 4. And it does seem that these 3 points, does seem that these 3 points lie on the line. And I see my x-intercept will be over here at x equals negative 15 fourths. That's almost negative 16 fourths or negative 4. We're just 1/4 away from that. So that would be negative 3.75 over here to the left. And it does seem like it's heading in that direction. So we also get kind of agreement with this, right? So sometimes we need to be a little bit creative or a little bit strategic about how we choose our coordinates so that we get something that we can plot without a whole bunch of hassle. Okay, so let's come over here and work on these two. So again, the same problems from last time, but I think going from the beginning and working all the way through now is helpful. So for each of these two problems, find 3 solutions, however you would like. You might want to strategize a little bit so that you don't have solutions that are super hard to work with, but find 3 solutions, 3 ordered pairs, and then draw the graph. So again, we'll take about 5 minutes or so for this problem, or these 2 problems. Okay, so there's let's review these two. There's a lot of different decent choices for this table up here. I chose to go with x equals 0, 1, and 2 because they gave me nice answers for y as well. I note that if I tried to find the x-intercept where y equals 0, I got an x-coordinate of 7/5, which is probably going to be a little annoying to graph, so I didn't really use that one in my graph. But I did kind of check it over here. I had an extra piece of information. I might as well just check that it kind of makes sense, and it does seem sensible. 7/5 is 1.4, and I see that my intercept looks like it could be about 1.4, just a little bit to the left of the middle of 1 and 2. I plot my 3 points, I get a line. Now, you could have had 3 completely different points. There's many correct answers here, but the line you ended up with should be the same as mine. Maybe you have, these 3 points or something instead. You might have had 3 different points, but you should have the same line as I have. The line that you ended up with should be the same because your line should include all of my points and my line has to include all of your points, right? Because the line has to include all of the solutions to this linear equation. And the way I drew it here looks like it's a string of Christmas lights or something, but and similarly for down here, right? If I think ahead, if I choose, say, x equals 0, I get 3y equals 8. That's not going to be so nice. So let me maybe put that down here. 0, what does y have to be? 3y equals 8. That would be 8/3. That's probably not going to be a super nice point to plot. If I choose, say, x equals 1, does 3y plus 1 equals 8 give me a nice integer solution? Well, no, not really. What about x equals 2? Sure, then y equals 2. So I might actually want to choose my y first and then my x, right? If I choose my y, then what's x going to be? X is 8 minus 3y. That's going to be a pretty nice x, right? If I pick y to be an integer, then x is 8 minus 3y is also going to be an integer. If I went the other direction, if I picked my x's first, then what would y be in terms of x? What if I wanted to solve this equation for y in terms of x? Remember when we did this a couple of chapters ago, this is where some of that previous material comes into play. I'd have 3y equals 8 minus x, or y equals 8 minus x all over 3. This might be an integer, it might be a fraction, right? When I picked x equals 0, this gave me 8/3. So in this case, instead of picking my x's and then figuring out what y is associated with it, I might actually want to go the other direction. I might want to pick y to be an integer, say like 1 or maybe like 3, and figure out what the associated x coordinate is. So when y is 1, x is 8 minus 3 times 1, x is 5. Does x equals 5, y equals 1 satisfy the original equation? Let's just check. 3 plus 5 is 8. That looks good. And then same thing with y equals 3. X is 8 minus 3 times 3. 8 minus 9 is -1. And we have 9 plus -1 equals 8. That seems good. I could also look for my intercept when y equals 0. When is y 0? That's when we are at the x-axis on the horizontal axis. So this is my x-intercept. When y is 0, x is 8. So I could use that one as well. I'll plot these 3 points, I'll graph my line, and then I'll just check against these 2 intercepts, make sure that this all makes sense. But I think really any of these 4, 2, 2, 5, 1, -1, 3, 8, 0 would be good options for plotting. You could probably find some others that where the numbers still aren't too big, where you have nice integer solutions. But I would, shy away from the ones that have a bunch of thirds running around. That's going to make the plotting a little less precise, a little bigger of a hassle, right? Like 8 thirds, I have to think, okay, how do I change that into a mixed number? If I do that calculation a little bit wrong, that's just another place that I could make an error. So x has to go between -1 to +5. So I'll just use tick marks in increments of 1 here. Y goes from more or less like 0 to 3. So again, just tick marks in increments of 1 would be fine. My 3 points are 2, 2, 1, 2, 2, 5, 1, -1, 3. That's kind of like right where I wrote the 3, so we'll just do this. Will it not let me select the 3? There we go. I'll just move my 3 over a little bit. With all of that, I think it would have probably just been quicker for me to rewrite the 3. Okay, so -1, 3. Now I draw my line between these 3 points. And then I'll just check the intercepts. When x equals 0, I'm saying that y equals 8 thirds. Well, that 8 is like 2 times 3 plus 2. So this is 2 and 2 thirds. And that does look like about 2 thirds of the way up from 2 to 3. So this seems about right. 8, 0. Well, 8, 0 is off the right side of my graph here, but it does look like that would be about right. If I went about 3 more units over to the right, would that line intersect the axis at that point? Seems pretty reasonable. So we do get kind of concordance with our other information. We get agreement, roughly speaking. Are there any questions so far? Okay, so the last thing that I want to talk about today, I think we'll actually skip this last little problem here, but the last thing I want to talk about today are 2 special cases. So we saw that we can have on our graph, we can have lots of lines. We can have a line like this that represents the solutions for a certain linear equation, a line like this for a different linear equation, a line like that for a different one, a line like that for another one. There are lots and lots of lines that can represent solutions to ax plus by equals c, in particular where a is not 0 and b is not 0. So when we actually do see explicitly an x term and a y term, we see an x term and a y term. We see an x term and a y term. Every one that we've done so far, we see explicitly an x and a y pop up. Now, what if I said this? What if I said, in the context, that I'm going to give you an equation representing a relationship between 2 variables, x and y. So this is a linear equation in 2 variables, x and y. I have 2 degrees of freedom I can start with. I have initially a plane, and I can have points anywhere in this plane. I can choose X however I want. I can choose Y however I want. If I gave you an equation like Y equals 3X plus 1, my graph looks something like this. Now I'm saying in order to satisfy this constraint, I can't just pick my ordered pairs anywhere that I want on the 2D plane. I have to pick them along a certain line, along the direction indicated by the graph of this line. Those are the ordered pairs that satisfy this constraint. I started, before I introduced this constraint, I could pick X and Y any way that I wanted on this two-dimensional plane. And then I introduced the restriction that Y has to be 3X plus 1. That said, a bunch of the ordered pairs no longer count. I can't say that those ordered pairs are solutions anymore. I can only say that these specific ones along this line are solutions. Now, what if I take that same idea? I have a relationship between two variables, X and Y. My solutions look like ordered pairs, X comma Y. At this point, I can kind of say that any point on this 2D plane is, in a sense, a solution. I'm going to introduce a restriction, and that restriction is going to look like Y equals 3. What does this mean? Now, to be very clear, this could mean something different in a different context. In the context of a linear equation in one variable Y, so maybe I had like 2Y equals 6, Y equals 3, we put a box around it, this is our solution. But that's a different context. If my context is being a linear equation of two variables, X and Y, where my solutions look like ordered pairs, first component comma second component, I've now introduced a restriction that Y has to be 3. If I consider a table of X's and Y's, if I have, say the ordered pair 1 comma, or say 0 comma 5, does this satisfy the constraint? Does it satisfy the constraint that Y equals 3? Well, no, because 5 is not 3. If I have an ordered pair like 7 comma 1, does this satisfy the constraint? No, because when I substitute in Y equals 1, 1 equals 3 is not a correct statement. But does 7 comma 3 satisfy the constraint? Yeah, it's an ordered pair that satisfies the constraint, because when I substitute in Y equals 3 in for Y, I get 3 equals 3. That's a correct statement. Does the ordered pair -2 comma 3 satisfy the constraint? Yes, it does. Does 0 comma 3 satisfy the constraint? Yes, it does. And maybe we see the pattern now. If my constraint is that Y equals 3, I fixed what the second coordinate has to be. Any ordered pair that looks like something comma 3 is going to be a solution, no matter what that something is. Is pi over 4 comma 3, that's a solution. It's a crazy choice for X, but as long as Y equals 3, as long as my second component is 3, then that ordered pair will be a solution. So one thing that's important about mathematical notation is that a similar looking notation can mean a different thing in different contexts. The solution in the linear equation in one variable, that variable being Y, saying Y equals 3, that's kind of the solution. That's the end of the problem. We're done. But if the context is we're dealing with a linear equation in two variables, and I tell you that that linear equation in two variables, X and Y, is y equals 3. In other words, the special case where a equals 0 up here, basically. Well, that is now a constraint on those two variables. X can be whatever it wants to be. It doesn't matter. As long as y equals 3, I've satisfied this constraint. X can be 7 or -2 or +5 or -1,000 or 0 or pi over 4. As long as y equals 3, that order pair will be a solution. So anything, comma 3 is going to be a solution. So for instance, if I look at my graph, for instance, 0, comma 3 will be a solution. Or 1, comma 3 will be a solution. Or 2, comma 3. Or -1, comma 3. And I see that my line, trying to keep my color scheme the same here across all these problems, I see that I get a horizontal line. I get a line that is parallel to the x-axis, that just looks like the x-axis, but moved up, in this case, up 3 units. I see that I have a y-intercept. I intersect the y-axis at height 3, so at point 0, comma 3. I actually see, though, for this special case where my line representing the solutions to this equation, this constraint, is parallel to my x-axis, do I get an x-intercept? Is there any x input that yields a y of 0 as the solution? Well, no. It's not just that like the x input would be annoying, like 17/3 or something. There's no intersection here. These are parallel lines, they don't intersect. So these special cases are a little bit wonky, right? In this case, we only have a y-intercept, not an x-intercept. We only intersect the y-axis, not the x-axis, because this horizontal line is parallel to the x-axis. And our constraint equation, our linear equation, looks a little strange because we don't explicitly see an x term. If you really wanted to force the issue, you could say, in this context, y equals 3 is something like 0x plus y equals 3. Since x is getting multiplied by 0, if I put in a 7 or a -2 or a pi over 4 or whatever, the 0 just cancels it out and it doesn't actually contribute anything meaningful to the constraint equation. So there is kind of a sense in which we still do have like a standard form, but just where a equals 0 in this case. So if we have an equation like y equals k, that gives us a horizontal line as our solution. A horizontal line that goes through 0, comma k, and it's parallel to the x-axis. As you might have guessed, we have a second special case. So this is like special case, number 1. We have special case number 2. What if I, again, in the context, linear equation of two variables, x and y. What if I had a constraint equation like x equals -2? Or if we wanted to force the issue, we could say something like x plus 0y equals -2. Here in my x equals -2, I don't explicitly see a y term. And remember, the context is we kind of start with a plane before we introduce the constraint. If I just said, I want you to represent two variables x and y on this coordinate plane, any point x comma y would work. But then I say, well, wait, I want to satisfy the constraint that x is -2. this is my constraint equation. It's not like 3x plus 2y equals 4. That might be a different constraint equation. But here I have a constraint equation that now, instead of any ordered pair satisfying my request, I only want those ordered pairs such that x equals -2. So for instance, -2 comma 0, that's good because that ordered pair has x equal -2. -3 comma 5, no good because here the x is -3. But -2 comma 1 or -2 comma 7 or -2 comma -3 or -2 comma anything is going to be a solution. So for instance, -2 comma 0 or -2 comma 1 or -2 comma 2 or -2 comma -1, these are all solutions. And my graph of the line is a vertical line located at x equals -2. Right. So x equals, say, m is a vertical line located at m comma 0. And again, note that we have an intercept. We have an intersection of our solution line with the x-axis. But if I asked, is there an intersection with the y-axis? In other words, is there a y value where the coordinate or the ordered pair 0 comma y is a solution? The answer is no, because in that case, my x coordinate is not -2. So we have no y-intercept. My line that represents the solution is parallel to the y-axis. It never crosses, it never intersects with the y-axis. So I have no y-intercept, but I do have an x-intercept. So these are our two special cases where, graphically speaking, our solution line is parallel to one of the axes, parallel to the x-axis, or parallel to the y-axis, or algebraically speaking, where we either can think of it as not explicitly seeing one of the variables, we only see one variable in the constraint equation, say y equals 3, or if we really force the issue, where the coefficient of one of our variables is 0. We either only see one variable if we write it in a simplified way, or where if we force the issue, the coefficient of one of the variables would be 0. So this y having a coefficient of 0 means whatever I put in there for y, it just gets hit by a 0, it gets zeroed out, and doesn't have any meaningful effect on the constraint equation. Are there any questions on anything we talked about today? So just a reminder that the WebAssign graphing tool can, take a little getting used to. I think after you do 2 or 3 graphs, it's pretty straightforward. But I would recommend just taking at least a glance through the graphing supplement posted on Blackboard, downloading it, maybe having it available as a quick reference, that if you're going through and you say plot something you think is the solution and it marks it wrong, or if you want to, clear something out or change something, you think, wait, how do I do that? You can have that kind of at the ready if you have any of those questions. All right, any questions on anything?